disappeared. How did that happen? Restore. Oh, that's good. Okay, fine. Okay, so who is this? And whose are these logarithmic tables? Did I show you these log tables? When you all came into the NCMH for the first time, did I show you these? Yeah. Actually, it was probably the turn of the CBT students today, because you've all had turns with the recording, so we're transferring it across ABT, ABI, undergrads, maybe the CDT. Maybe not down there, I don't know, but regardless, you've all got access to the video material. Good. So, who is this? And these are his log tables. Any clue? Is Logarithmische Rechnungstafeln, these German log tables. And there's a message in the front of them. It says, "Tillille kvantivapen på skottdagen fra deres huset." Any Swedish speakers here? No. Snacka svensk. And there's a letter to Mrs. Svedberg here. So these logarithmic tables belong to Mrs. Svedberg. And translating from the Swedish, "Tillille kvantivapen" is "to my little puppy dog," or "kvantivalpen" actually is quantum puppy, so packet puppy it literally means, but "to my little puppy dog." På skottdagen, and skottdagen is literally translated to "on the shooting day." And the shooting day is a leap year day, so 29th of February, when traditionally people, generally richer people, would go, shooting grouses and all these sort of things. Anyone seen the film Queen Victoria, where she goes to Scotland and shooting these poor little birds? Anyway, that's shooting day, på skottdagen. So, to my little puppy dog, on shooting day, fra deres huset, from its master, from your master. So, and it's dated 29th February 1940. So this was a gift from this man, who is Theodor Svedberg, who won the Nobel Prize in 1926 for the invention of the ultracentrifuge. And it's a very powerful method. It was the method which showed that proteins were discrete entities, discrete molecular entities, as opposed to a colloidal continuum, as was thought by many people before the 1920s. So he was responsible for the invention of the ultracentrifuge, the analytical ultracentrifuge, which has become a very powerful technique in biomolecular science, and deservedly got the Nobel Prize in 1926. And these were his logarithmic tables, which were a gift actually to Mrs. Svedberg, his wife, and somehow they got left in Cambridge in 1940. I think Mrs. Svedberg, which you worked out was Inga-Britta Svedberg, or Inga-Britta Eriksson, her maiden name, former PhD student of Svedberg, and she left these in Cambridge in 1940. Hello, Jake. I won't go into the details why they were left in Cambridge. That's an interesting story in its own right. But they were left there, and I inherited these in 1984. That's when I used to be a postdoc there, and that's when I came here in 1984. So I was 28 then, so you probably work out how old and decrepit I am now. Not quite on the Zimmer frame yet, but that was an interesting period. And what happened was that when I came here, my old boss at Cambridge in the biochemistry department, it used to be the colloid science department, he was retiring at the same time I came here, and he had a whole pile of books which he gave me. He said, save them or throw them away, whatever you want. So I was going through these books, and I came across these German log tables, and they went straight in the throwaway pile. I mean, how would you use German log tables today? Then as I threw them out, this letter dropped out, Mrs. Svedberg. So I immediately, oh, this is interesting. And then I got this, the Swedish translated by a friend of mine who could speak, a Swedish friend. And so I decided to keep it. It's very interesting. So these log tables belong to a famous Swedish Nobel Prize winner. And as I'll show you later, we have three modern ultracentrifuges, not like the old ones that Svedberg used. But the new generation, or that as then the new generation, then this is 1990. Okay, things were still new even then. And we got one of these instruments free from Beckman, but I had to go on as part of the deal, we do test experiments. It cost about £300,000 now new, and had to go around Europe giving talks about the rebirth of the centrifuge. And one talk was at Uppsala in Sweden, which is where Svedberg did all his work developing the ultracentrifuge. And it was like being invited to give a talk on how to drive a car to Michael Schumacher or Sebastian Vettel or Lewis Hamilton, you know, people who know. And going to Uppsala to give a talk on the ultracentrifuge was quite an experience. By then, 1989, 1990, it stopped all that work, and this was a talk on the rebirth of the centrifuge. And at the end of the talk, to all these Swedes, I took these log tables with me, and I thought, finally, actually, they might ask for them. I said, these are the log tables that belong to Svedberg. And there was great interest, and I thought they were going to ask for them back because they have a museum, Svedberg Museum at Uppsala, commemorating the work that he did. And then I said, well, actually, they're not Svedbergs. They were a gift to his wife, and that started a bit of a debate, actually, and we found out that he'd been married several times, and they were trying to work out, he married a series of PhD students, so trying to work out which one. So that was a big surprise. The other surprise was, at the start of the talk, some people started laughing as my name was, or chuckling as my name was announced. Then I found out later that my name, Harding, means something funny in Swedish. It means a tough guy, a skinhead, a sort of football hooligan. We're confronted with this man who had the name of a football hooligan, which, as it transpired, it was clear that although I was a football supporter, I wasn't going to smash the place up, which was a great relief. And then also on that tour, did I tell you this story? That I gave a talk I was invited to give a talk in East Berlin in 1989, and this is before the Berlin Wall had come down, and they gave me a choice. It was, I could give the talk in English with a mit Übersetzt, that's with a translator, or I could give the talk in Russian. Yeah, or auf Deutsch in German. You sure I haven't told you this story before? No. Anyway, I've been going to night school class in German for a bit, and my night school teacher said, "Oh yeah, go for it." So I offered to give the talk in German, and it's the only time I've given a lecture or a talk in a foreign language. And this was the former communist East Germany. Actually, by the time I gave the talk in April 1990, everything had changed. The wall had come down. It was still the German Democratic Republic. It was still East Germany, although the wall had come down. Formal union didn't take place till after that, and it was a very exciting time to go. If you go into my office, you'll see a piece of the Berlin Wall and an old East German flag, which I got the piece of the wall myself actually at Potsdam. Exciting times for a young scientist. So it was very exciting, and my talk was announced all over 2 institutes, one in East Berlin called Buck, which is now the institute, formerly Academy der Wissenschaften, the DDR or something, is now the Max del Drucker Center for Molecular Biology, a very famous institute. And then the other talk was at Potsdam, or Teltow, which is near Potsdam, at the former Colloid Institute. So my talk in German was announced all over the institutes, and it was, well, in English, it was the Analytical Ultracentrifuge Spins Again. I thought it was a very catchy title, which, the instrument coming out, getting going. And unfortunately, there was a mistranslation in the title, a very serious mistranslation. So the Analytical Ultracentrifuge Spins Again, I translated to Die Analytische Ultracentrifuge spinnt wieder. Anyone know German at all? No German speakers?
Yes.
Yeah. So you know what that means then?
Ish.
Okay. Well, the problem was with the word spint. So die Analytische Ultracentrifuge spinnt wieder, which I thought spint meant to spin. It did in 16th century German, but in modern German, it meant something else. And it means to go crazy, to go mad, go stupid. So the ultracentrifuge goes stupid again, is what and they were too polite to tell me. So this is until the end of the talk. You didn't realise it was a mistake, no. And so that was a very interesting experience. And my mother used to say, never try to be too clever. And that was a case of me trying to be too clever. So that was the only time I'd given a talk in German. I can almost remember it off. I remembered it. I learned it off by heart, basically. And I can still remember this almost word by word. Okay, so that's just a lesson. Of course, now everyone speaks English, correct? Even in Japan, and maybe not everybody, but in science, people speak English in China and Japan and Malta and everywhere. Yes, in Mexico. Yep. So it's there's no need now for people to speak in a different language, but it was exciting. And also at that time, people from other countries, Japan, China, South America, Spain, Germany, they would struggle to speak English a little bit and mispronounce some words. But now I think everyone speaks English in science. We're just lucky as English people. That's the case. That's an interesting background behind Svedberg. So Svedberg, Nobel Prize winner of 1927. Did I say 26? For the invention of the analytical ultracentrifuge. As I said, it's a technique which revolutionized molecular science, polymer science, all those years ago, and it was a technique which showed that proteins were discrete molecular entities. Right, this is the Svedberg ultracentrifuge. If you go into his laboratory, which is preserved now as like a museum in Uppsala, you won't see any. You're looking for an instrument, some boxed machine or whatever. You won't see it. What you'll see is a room full of pipes, pumps, refrigeration devices, and cables. The whole room is an ultracentrifuge. So you're walking into basically the room as a centrifuge. And here is the vacuum chamber, because these things are on a very high speed, so you have to have a high vacuum. So here's the vacuum chamber. Let's get... is it better? It's better. Okay, so here's the vacuum chamber. This is the optical bench containing optical components, and this is a photographic plate where images from the experiment were recorded. There were no computers and things then. And this is a vacuum gauge which records the vacuum in the vacuum chamber, and all sorts of pipes and stuff here which drive the centrifuge to very high speeds, up to 50, 60,000 revolutions per minute. Things have changed a little bit since then, as you'll see later. So, sedimentation analysis of macromolecules. It's a very important technique, very versatile technique. It's an absolute way of getting molecular weights. Last week with electrophoresis, we dealt with a relative way of getting molecular weights. By the way, with the undergrad group, we had the electrophoresis demonstration last week, and that went okay. And I think with the Abbeys as well, we had that concentration demo as well, with the specific volume demo. Yes? And just to reiterate that there are no, as far as I know, there are no living creatures on Mars. Okay, so that Martian rock lizard protein was a hypothetical. It wasn't real, just to make absolutely sure everyone's clear about that demonstration of the big bar calculation. So we met electrophoresis, an absolute relative method for getting molecular weights. Now we're going to meet sedimentation in the centrifuge, which through this method here, Sedimentation Equilibrium, provides an absolute way of getting molecular weights, the weight average molecular weight. But this other variant, velocity sedimentation, is also very, very important as a way of assessing the heterogeneity of a material, how polydisperse a material is, and also for getting conformational information about molecules. For the Abbey and ABT group, this method is the gold standard method for assessing the integrity of preparations of monoclonal antibodies. So this is the gold standard method. And the reason is because it separates through the centrifugal field materials of different size and analyzes with the special optical system the components which are separated without the need for a separation medium like a gel in electrophoresis or chromatography. So it's a very important technique for checking the molecular integrity, how pure a material is in biopharma, food, environmental science. Okay, got wide application. Okay, so an ultracentrifuge. A centrifuge which spin things, and you can separate because of the higher G-force you create by spinning things at high speed. Ultracentrifuge means very high speed. So up to 75,000 revolutions per minute. So in preparative ultracentrifuge, used to separate materials, purify them, we can get up to speeds of 75,000 revolutions per minute. An analytical ultracentrifuge is a special ultracentrifuge which has an optical system built in. So as the material sediments, they sediment through special containers called cells where you can shine light through, and you can monitor the sedimentation process using these special optics. And from that, you can get information about the sizes, shapes, and interactions of the molecules. So these analytical centrifuges tend to go up to a maximum of 60,000 RPM. They don't go higher than that because of the strains on these special cells with windows and all this sort of stuff. So usually 60,000 RPM is as high as you go with analytical centrifuges. Analytical for analyzing the distribution, not just of proteins, but other molecules like polysaccharides, glycoconjugates, and nucleic acids. And there's two types of sedimentation experiment. There's sedimentation velocity, which high speed, so you go at the high speed appropriate for that molecule, and from the rate of movement, how fast it goes. Okay, it doesn't happen within seconds. These things, because of the tiny molecules, you need a very high G-force to get them moving, but they do move, and very slowly, but they still move. So you follow the progress of the solute-solvent boundary as the protein or macromolecule sediments. And this gives what's called the sedimentation coefficient, which is a measure of the size and shape of the molecule. So your 30S ribosomes, your 70S ribosomes, your 11S soybean globulins, those S values are the sedimentation coefficient expressed in the units of Bergs. And you'll see what they are in a second. The second type of experiment is sedimentation equilibrium, where we don't run at such a high speed. We run at lower speeds than for velocity. And what happens at lower speeds, as you, under high G-force, you push things along the centrifugal field, okay, in the direction of the field, things are pushed towards the bottom of the container under this G-force. Now, there is another force which tries to push everything back. It doesn't like things all stuck at one end. That's thermodynamically not so great. It wants everything spread out. So what's that sort of force, that process which wants to push everything back? Diffusion, okay? So diffusion wants to push everything back. Now, at very high speeds in this, the diffusion forces are small compared to the sedimentation forces, so the material will sediment. But if you run at lower speeds, where the G-forces aren't quite so high, then the two forces, sedimentation and diffusion, become comparable. And then after a period of time, you get a balance or equilibrium between the two forces, and you get not everything being pushed down to the bottom, but you get a distribution of material. So low material, low concentration of the meniscus, building up to a higher concentration at the bottom of the cell. And we call this experiment sedimentation equilibrium. So when the forces come to equilibrium, the pattern stays constant. And because there's no movement, there are no frictional forces coming into play, so it doesn't matter what shape the molecule is. The distribution is only a function of molecular weight. So it's an absolute way of getting molecular weight. Sedimentation coefficient, or this technique for looking at the heterogeneity, purity of the preparation, how pure the monoclonal antibody is or the protein is, nutrition or environmental science, or how polydispersed your polysaccharide is, spread. And that gives the purity and also the shape of the molecule. Can also give the mass as well, but you have to make an assumption over the shape. This technique gives you the absolute molecular weight. So that's a very powerful combination of methods with the same equipment. And this is this instrument, the Optimum Excel I, which was new in 1989, 1990. We got the first ever instrument made. We got serial number 1 for free. And now there's approaching 1,000 of these instruments worldwide. So it's quite good for us to get the first ever, especially with it being American, because normally Americans like to sort of keep things in America. If you're not American, you don't count. It's like when the Beatles went to America for the first time, and they were criticized because they didn't have American haircuts, short haircuts. And then John Lennon said, well, actually, we're not American. Tried to make it clear to the Americans that they seem to expect everyone to conform to what they do. That's not the case. So it was quite a coup getting this instrument here. First, we'll talk beta instrument, that means test instrument in D. And it looks rather unremarkable, really, isn't it? It doesn't look like an instrument, not like Bergs. It looks more like what I have over there in the laundrette. Yes. A washing machine, isn't it? Someone said it looks like a washing machine with spin dry facility. But if you put your clothes in there, you won't get them back. You probably have a fire. Spin dry at 75,000 revolutions per minute. Fun. So it looks quite unremarkable, but inside there's very complex electronics and optical systems, mechanics, it's all built in, and linked to a computer. That's what computers looked like in 1990. That was taken in our lab in the NCMH, which has now been knocked down, where the barn building is. That's where the old NCMH labs used to be. Now they're at the back of the campus. I think all of you have been there, I think. Yeah, at some stage. So that's what it looks like. Disappointing, really. But take the front off it. Okay, not quite as simple as that. This is a schematic. And what you have is a rotor containing these containers. Is that bad English? Containing these containers, which includes these metal containers called cells. And these cells have, I should have brought one with me, but I'll show you anyway with a demonstration later, have transparent windows at either end. So what you do is you shine light at the appropriate wavelength through the cell. Obviously, when it gets to that part of the orbit, the light isn't moving as well. The light's fixed. So when it gets to that part of the orbit, light goes through. It's pulsed through. Could be a laser, could be xenon arc, and then interacts with the molecules. And then the patterns that accrue, the light comes through a system of slits, lenses, and the optical patterns generated are picked up by a detector. It could be a photomultiplier or CCD array, and then the information is passed to the computer for processing, and that's exactly what's happened here. Okay, so that's, in simple terms, how the ultracentrifuge works. And of course, this all takes place in a high vacuum. because at 60,000 revolutions per minute, or even at 3,000 revolutions per minute, if it's done in air, things get rather hot, and things get very hot actually. You want to see what happens when the vacuum fails. It's very, very spectacular. It doesn't happen now in modern instrumentation because there's all these sensors and things. But when I started off as a PhD student and postdoctoral researcher, we had the occasional accident. And even when we were here, vacuum had failed or the drive had broken. And there's one instance when my office was upstairs in this building and centrifuges were all downstairs. And they weren't these instruments, they were older instruments. And the drive had broke, and there was a banging. I was upstairs in my office, had this banging noise. And this student runs up, Romana, I think his name was, Dr. Harding, I think there's a problem in the ultracentrifuge lab. So we ran down, and there was smoke everywhere, and there was chaos because this particular instrument called an MSc Centriscan, the drive had broken, the vacuum had failed, and there were these little wheels that are normally kept up, but we dropped down when we're moving, to our place. And the force of the collapse had dropped the wheels down, and this instrument was chasing the students around the laboratory. So I wasn't very popular in the department because before we got the new centrifuges, we basically accumulated old ultracentrifuges that everyone was throwing out in the 1980s, and we got them for nothing basically. And when you get second-hand instruments, so they cost nothing. They're not always. Some of the components aren't always perfect, and it was actually a failure of a component in the drive which caused this. But these things don't happen now because there's so many modern instrumentations. There's all these sensors which stop these accidents from happening. And there was another incident where I was due to go to Cambridge to see my old boss, and Sedimentation Equilibrium runs take a few days to run, 2-3 days to run. So you run them overnight. So I set the run up the night before, and I popped in the morning to check everything was okay. And I opened the door, and this tsunami of water came out, whoosh. And what happened was that the water coolant system had blown off from the pipe at the back of the centrifuge. And because there was no drain in the lab, and the door was almost a perfect seal, the water just built up. And then it's got a clean lab. All the poor old spiders and things got washed out as well. But it washed out and it went into the professor's office next door, which wasn't very good, and stained his carpet. So, yeah. Again, those things don't happen now. So if you set things up incorrectly, the run also, there's a component which is weak, it won't run. Right, so that's a bit of background. Let's do some science now. So this is the container. It's about 4 centimeters long and about 1 centimeter in diameter. This is the centrifuge cell. It contains 2 channels, one for the reference solvent and one for your solution. So reference solvent is whatever this protein or polysaccharide is dissolved in. And then you've got these little holes here which you can inject your solution in. And then these are plugged before they go into the rotor. The cells are balanced like any other ultracentrifuge. Preparatory centrifuges use these plastic tubes, but for analytical centrifuges, you use these special metal cells, but they have to be balanced. Otherwise, you have an accident, or in modern instrumentation, it wouldn't run because the sensor would check that your rotor is not properly balanced, and you just wouldn't run. So There's our reference solvent, and here's our solution. And you don't fill it completely, you leave an air gap at the top, a bit more solvent than solution. And after a while, under the influence of the centrifugal field, a boundary will appear, which, as the material sediments, it leaves clear solvent behind. Okay, as a protein sediment or polysaccharide, it'll leave clear solvent behind. So if the direction of centrifugation is this way, then as time progresses, this boundary will slowly move towards the bottom of the cell. It takes a few hours for it to shift from here to here until everything is piled up at the bottom of the cell. Now, if you scan across this cell, so your optic scans across here, and if it's a protein, you could use ultraviolet optics. Tuned in at what wavelength? Those that had the concentration demo last week should know this. What wavelength were we tuning into for the protein demonstration? What do we set it as? Yes. What? Anyone? Yeah, 280, spot on. Because what groups absorb UV radiation at that wavelength? Yeah, tryptophan, tyrosine. Yeah, so we tune in at 280 nanometers. And then if we scanned, what we'd find is at that particular moment of time, we find that there'd be no absorbance in this part of the cell. We're scanning across here. And then you get a boundary, and then you get the protein absorbance here. So this is distance from the center of rotation, which will be here somewhere, as it rotates around the axis of rotation. And the rate of movement of this boundary per unit centrifugal field, that should be, how does that come out? There should be a line there. It's rate of movement divided by unit centrifugal field. So the rate of movement of the boundary per unit centrifugal field gives what's called the sedimentation coefficient, which is the symbol small s. Okay, small s. And what all this means here is that when comparing sedimentation coefficients for different molecules, because the sedimentation coefficient will depend on what solvent you're moving through, sodium chloride solution, glycerol, which is quite viscous, or cesium chloride, or tris buffer, because it'll depend on the buffer and the viscosity of the buffer and density of the buffer. We normally normalize. That's bad English. We usually normalize the standard conditions or standard solvent conditions, which are the density and viscosity of water at a temperature of 20 degrees centigrade. So there's a simple way of correcting a sedimentation coefficient to these standard conditions. It's done on the computer now in any case, so it's quite straightforward. And also the zero means that usually we have to correct for our old friend non-ideality. Remember that? Gets in the way all the time. Yeah. So normally we correct for non-ideality by making measurements of a series of concentrations and extrapolating back to zero concentration, or working at very low concentrations where these non-ideality effects are very small. Okay, so that's what that little zero means. Now, it's complicated, goodness me. If we're working with polysaccharides, then they don't absorb in the ultraviolet. So we can use refractometric optics and refractometers and things. But these particular refractometric optics are based on what's called Rayleigh interference. And what you have is, instead of this boundary, which moves towards the bottom, you have a series of fringes, if you look at this one here, it looks like that one there. So you have these multiple fringes, and the point of inflection corresponds to the center of the boundary. So we can use interference or refractometric optics for any macromolecule, proteins, polysaccharides, or whatever, and it generally gives more accurate information because instead of one line here, you've got many lines in which you can take an average of. So interference optics, although it looks more complicated, gives you a more accurate result that can be applied to any macromolecule. And the unit of sedimentation coefficient is the Svedberg. If you invent a technique, then you can have a unit named after you. That's okay? Yeah? The Svedberg. And one Svedberg, capital S, sedimentation coefficient is small s, capital S, is the same as 10 to the minus 13 seconds. So one Svedberg is 10 to the minus 13 seconds. Right, carry on. So here's an example. This is for the nutrition people. This is beta-lactoglobulin, which is our favorite milk protein. And what's special about beta-lactoglobulin? It normally exists as dimer. That's right, dimer. It's a dimer in the normal conditions. So beta-lactoglobulin dimers, this is at 25 degrees centigrade at 50,000 RPM, recorded at 280 nanometers. Is that what you've got on your sheets there? Yes. You can see that's my mobile phone. Always switch your mobile phones off when you come to a lecture. Or if it's not switched off, remember where it is, so you can easily switch it off. Right, so this is the sedimenting boundary recorded every 20 minutes. So from the rotor speed, so the rate of movement of the boundary, how fast this moves in centimeters per second, divided by the centrifugal field, which you can work out from the rotor speed, gives you the sedimentation coefficient. In this case, it's 2.97 plus or minus 0.03 Svedbergs. This is an example of sedimentation velocity using absorption optics. And this radius here is the distance from the center of rotation. So how far this point in space is from the center of rotation of the centrifuge. Okay? That's how you get sedimentation coefficient. And there we go. It's velocity divided by the centrifugal field. So V divided by omega squared R. So omega is the angular velocity of the rotor. Okay, how many angles in the circle? 360 degrees. How many radians is that? 2 pi. Yeah, 2 pi radians. There's 2 pi radians in a circle because the perimeter is 2 pi r. Yeah, remember that? So 2 pi divided by 60 converts revolutions per minute to radians per second. Unit radians. Sometimes rads per second, but rad, it's not the same rad as in radioactivity. That's not nothing to do with radioactivity. Right. radians per second. Right, so if you work out the sedimentation coefficient, these are some of the values which you corrected to standard conditions, density and viscosity of water at 20 degrees centigrade. So lysozyme, 1.91 10 to the minus 13 seconds, or 1.91 Bergs. Bovine serum albumin, 5.01 Bergs. Fibrinogen, longer molecule, more frictional resistance. Sedimentation coefficient and larger, 7.9 10 to the minus 13 seconds, or Bergs. There's a misprint here. Something's missing. What's that? Of albumin. Yeah. Right. So I have to correct that. So, but these are some examples of sedimentation coefficients of proteins. Okay, if that phone makes a noise again, every time you hear a noise, it means someone's sending me an email. That's how many emails we get. So if it does it again, I'll switch it off. Right, the sedimentation coefficient, after you've measured it, is related to the molecular weight and shape by this equation here. Are we okay going on for another 10, 15 minutes? And then we're more or less done. And then we have a break in the demonstrations. Or do you want 5? I tell you what, I might have just a 2 or 3 minute break when we finish sedimentation velocity, and then we'll reconvene and do equilibrium. And then have a longer break later on. Okay, so sedimentation coefficient is a constant times the molecular weight to the power 2/3 and divided by this ratio here, which depends on the shape of the molecule. So sedimentation coefficient depends on the size by the molecular weight, and also on this term here, which depends on the shape and also depends on the size as well, as you'll see in a second. So this is the axial, this depends on the what's called the axial ratio of the molecule. I think we did that. Did we do ellipsoids earlier on? Yeah, long axis to the short axis. Okay, right. Well, this depends on the shape, and the constant depends on the density, viscosity, and the protein or macromolecular density, or partial specific volume, because that's the reciprocal of density. So the constant depends on the solution density, the viscosity, and the protein or macromolecule density or partial specific volume. And as we said, the sedimentation coefficient for comparison purposes is corrected to standard conditions, that is the density and viscosity of water at 20 degrees centigrade. So when you see S20, it means, or S20W, it means it's been corrected to standard conditions. So we mentioned also, where are we? S0, yeah, I mentioned that we corrected for non-ideality, and the way we do that is we make measurements of the sedimentation coefficient at different concentrations and extrapolate back to zero concentration, particularly S0 or S0 20W if we extrapolate the normalized sedimentation coefficients back to zero concentration. And that's it for velocity. Do you want a 1 minute break or 2 minute break, or should we go straight on with equilibrium and get it done? Who would like a brief 2 minute stretch? vote? No, yes, okay. So what's just a 2-minute break? Literally, just don't go over to the coffee place. Just have a little stretch. So we'll reconvene at 3 minutes time, and then it shouldn't take more than 10 minutes to cover sedimentation equilibrium, and then we'll split you into groups for the demos. Anyone wants to look at these wonderful log tables? They can.
I have a question about this. For this, most of us are not sure if you have to like do the log of this and like use Excel and answer it, or just depending on this one, talk about the molecule itself, the protein.
Right. So maybe I should make the announcement at when the class comes, but I'll do it. But just for you, basically, what you're required to do is this axis is logarithmic axis. There's no need to take logarithm. It's already in a logarithmic form. Yeah, because look, see the way the numbers are.
Yeah.
They're not evenly spaced. They go up in a logarithmic scale.
Oh, okay. So this is the logarithmic one.
Yeah. So what you've got to do is work out the relative mobility for the protein in the two different states of treatment, and then read off from the calibration plot.
So one is like 2, which is like almost between 6 and 7.
Yeah.
And then it moves to like 5 after this disulfide, which is almost like a 3-ish.
Yes.
Around the coursework.
Yes, that's right.
I think as well, just to avoid a bit of confusion, there's a slight error on it.
Why?
On the y-axis where it gives the relative molecular weight, it gives it in units of 10 to the minus 4.
That's not an error.
I think it's going to be 10 to the 4 though.
No, it's not. The axis, that 10 to the minus 4 times m is the label of the axis. It tells you what those numbers are. So 10 to the minus 4 times m, if it says 4, then that means 10 to the minus 4 times m is 4. Right?
I was like, because I was going to
It just labels the numbers. So these numbers are 10 to the minus 4 times m. So therefore, m is, if 10 to the minus 4 times m is 2, therefore m is
4 times 10 to
is 2 times 10 to the power 4. Yeah.
10 times 4.
So there's nothing wrong with the axis. It's absolutely correct. That's why I did it that way.
Okay.
For that question to be asked. And this year it's Jake that asked that question, which is that clear?
Yeah.
So that label on the axis tells you what those numbers are.
Okay.
Yeah. And a warning: if we get back non-sensible answers, that is molecular weights that are less than 1, then that gets penalised. Right. All right, Jake?
Yep.
When was the hand-in date of the coursework?
Hand-in date, folks, was it the 26th of November?
Okay.
Yeah, 26th, yeah.
And then online.
Yes. So on Friday this week, what date's today? So we're about 12. Yeah, on Friday this week, I'll put an announcement on the Moodle which gets sent through, and I'll set up a way on the Moodle where you can submit your work, like with other Moodles, okay?
Thank you.
But it won't go up until Friday.
If I've done it by hand, can I just scan it in and then upload that? Or do I
Yeah,
join
scan
you
it.
right
Yeah,
now?
with the coursework, yeah, please do it by hand. When you do equations and things and graphs, maybe the Excel graph you could put that in, but yeah, do it by hand. Otherwise, you've got to mess about with subscripts, superscripts, risk getting marks taken off because you've not got the subscript in properly. Do it by hand.
Okay. Cheers.
Yeah, and then scan it in and send it as a PDF, not as a Word file.
Okay.
Anyway, when I give you the announcement, I'll explain what you should do. Yeah, and I'm deliberately not putting it up now because people tend to do the things before they've had the lecture. You know what I mean? And there's also a question based on the centrifuge lecture.
Yeah, it's the last one, because I'm doing the undergraduate course.
Yes, they all do that. It's all right.
Oh, okay. Right.
Yeah.
Wait, thanks.
Good. What time do you take?
So,
Right. If you're not back yet, please raise your hand. Are we all back? Who's missing? There's a. Michelle.
About the literature review.
Yes.
Is it okay if I send you, once I start writing it, is it okay if I send you some drafts of
Yeah, that's right.
sections once?
You're a PhD student now, so you do that.
Yeah,
Okay.
it's
And then me and Rob will look at it and check it through. But don't forget, it's Rob's inaugural next week.
It's next Wednesday.
Next Wednesday, don't miss that.
Yeah, yeah.
Okay.
It's 6?
Is it 6 to 7 or 5 to 6?
Or 5. I think it's at 5.
Yeah, it's in the chemistry. I think it's in the chemistry building.
I
I'm not
think it's
sure.
at the chemistry building. There's
Okay.
a reception at the foyer.
Yeah, should be good.
Yeah.
Is that, if we get 6, is that like this one and you?
Correct.
Yeah.
Correct.
Okay, thank you.
Okay, we all back now? Anyone not back? You're not back. Right, sedimentation equilibrium now. So this is a different technique using the same instrumentation. And as I said at the start of the lecture, it's slower speeds, so the forces of sedimentation one way are balanced by the forces of diffusion the other way. So this is a velocity experiment. At any given time, you've got this boundary between the solution and the clear solvent left behind. And this is the distance from rotor center, and the rotor center zero value will be here. These values here range from about 6 to between 5 and 7. And with time, what happens is that the boundary tends to spread out a bit, and that's because of the effects of diffusion. So even at very high speeds, diffusion does have an effect, but all it does is spread the boundary out with time. But at much lower speeds, diffusion forces become comparable with sedimentation forces, and instead of getting that, you end up getting, it takes a while, maybe a day. Or for polysaccharides, because they're very slow moving, could take between 2 or 3 days to get to equilibrium. But these forces get to equilibrium, and you end up with a steady state pattern of a low concentration at the meniscus, gradually building up to a high concentration at the bottom of the cell. And it stays put, so it doesn't change. So you wait until you get a final steady state pattern, and then you can analyze the data. So what we popularly do is plot the log of the concentration, either to base E or base 10, and plot that as a function of distance squared from the center of the rotor. And the reason for that is that if you've got a single solute system, like ovalbumin, like beta-lactoglobulin dimers, it's all dimer, it's a single solute. If you've got a mixture of monomers and dimers, then that's not single solute. But if it's all dimers, it's single solute. It's hemoglobin, tetramers, it's myoglobin. Molecules like that with a single molecular weight, you'll get a straight line if you plot log concentration against distance squared. And the slope gives the molecular weight times a constant. Okay? And if you've got a heterogeneous or polydispersed system, then what you get log C against distance squared, distance is r, then you can get a curve. But you can get an average slope, and that will give you an average molecular weight, which is what sort of average? Weight average, that's right. So for a heterogeneous system, log C versus r squared is curved. Can you read that bad writing? The apologies for the record. We haven't got this on record, I'm afraid. Slope equals the average slope so the curve, the dark curve is the actual data, and that's supposed to be a straight line, by the way. That the lighter curve is a straight line. That gives the average slope. That gives the weight average molecular weight. So that's the simple way in which we analyze equilibrium data. From the slope of a plot of log concentration against distance squared, we get the weight average molecular weight, which is an absolute molecular weight, not requiring any calibration standards, unlike electrophoresis. Yes?
What do you mean by curve? Like here in the picture it says like a straight line, that's for the normal.
Monodisperse, single solute system, you get a straight line.
Okay.
Okay.
So for a heterogeneous system,
You get a curve.
And the other drawing would be a straight line then.
This is a straight line which you get for a
So
single
like,
solute.
if it's curved when it's log C, when it's C for the heterogeneous system, would it
Yeah,
be
it's
less
also curved for log C. So it's always curved for concentration against distance, yeah.
for both kind of systems?
Both kind of systems. When you take the log of the system, this is curved for a single solute, you get a straight line. For a heterogeneous, it will still be a curve. Not quite as curved as that, but still curved. And then you take an average slope, which gives you the weight average molecular weight, as opposed to the number average molecular weight, which you get from osmotic pressure. Great, so that means we've got a way of getting weight average molecular weight. We've got a way of getting number average molecular weight from osmotic pressure. So when we order our pectins for our dog food and things, lecture you had on different molecular weight averages, we now know how we can get the different averages and how we can work out polydispersity, which is the ratio of weight average to the number average molecular weight. Great. Okay, it's not quite as simple as that. Let's just carry on. Now, the optics we use to record the patterns, again, we can use absorption optics if it's a protein. Provided the absorbance is, well, when the instrumentation first came out, the optics were not as good in terms of the Lambert-Beer limit compared to a conventional spectrophotometer, but now the optics are fantastic. So as long as we keep below the normal Lambert-Beer limit, which is 1.2, 1.4, then the absorbance is directly proportional to the concentration. Okay, and if you dilute, of course, you can lower the absorbance values. The difficulty is, although your starting absorbance can be within the Lambert-Beer limit, by the time the equilibrium run is finished, then at the bottom of the cell, the absorbances could be much higher. So you have to be aware of that. And if there's any problem, you just switch to the other optical system, which is interference. Yeah. So absorbance is the easiest to use, providing the absorbance is less than or equal to 1.2, 1.4. And that's the equation again, the Lambert-Beer equation. So it's easy to convert the scans into one of concentration versus distance versus the against the rotor from the rotor center. So the molecular weight m equals d log c dr squared. In this case, we've got logs to base e. So what that is basically the slope of a plot of log c against r squared times a constant. Well, the constant is 2 times the gas constant, R, times the absolute temperature, T, divided by 1 minus V bar, which is our old friend, the partial specific volume, and the solvent density, rho, which for water at 20 degrees is 1, times the angular velocity squared. So that is the constant here. So if we know these parameters and we measure the slope of a plot of log concentration at distance squared, we can get the molecular weight. And in the coursework example I've set you, that's what you are asked to do. One important thing, though, is that if you use absorption optics, there's no need to convert absorbances to concentrations. You don't need to know the extinction coefficient or the path length of the cell, because d log c dr squared is the same as d log a dr squared. It's because of d log ec dr squared. D, by the way, doesn't mean d times. D times. D dr, that's just the differential form. So it means a change of log c with r squared. What's my... Threw it in the bin, didn't I? Let's try that. Oops. Right, d log c dr squared, which is the same as d log c dr squared, where log stands for natural logarithm, okay? And that's the same as 1 over c dc dr squared. So the units of c cancel. So it doesn't matter if the units of c are in gram per mil, kilogram meter cubed, absorption units, fractometric units. It doesn't matter what the units of concentration are, the units of concentration cancel out. So there's no need to convert the absorbance units into weight concentration units. There's no need at all. Right? That makes it even easier to do. So that's how we get molecular weight from sedimentation equilibrium using absorption optics. And isn't handwritten things, do you think that's nicer to follow, easier on the eye than having Arial font, Times font, all this stuff? You disagree? Okay. Don't you miss little crossings out? Like, look at this. See, the discussion we had around that, you wouldn't get on a nice clean type slide. I like it. Right, so what about other molecules which don't have a chromophore, so polysaccharides? We can use refractometric or interference optics. What's called interference is you have two beams of light, one going through the solution and one going through the solvent, and these are combined optically by lenses arranged in a particular way to give these stripy patterns. Okay, these little stripy patterns. So here's our centrifuge cell looking down, okay? And the two compartments, we've got the solution compartment and we've got the solvent compartment. Now, note there's a difference between the velocity experiment where we filled these compartments, more or less, left a little bit of an air gap at the top. Remember? This time, we've only put a small amount of solution and reference solvent in. Right? And the reason for that is that if we keep the columns short, then it gets to equilibrium faster. If you have a long column, it takes ages for the forces to get equilibrium, but by having a small column, the forces come to equilibrium faster. Because we can't be bothered waiting days for these things to come to equilibrium. You know, science progresses faster. You can't wait a week, but we can wait a day, or maybe 2 days, 3 days with polysaccharide. It would take ages if we had full columns. So we have short columns of solution and the reference solvent, and then these interference patterns are produced. So when you've got no difference between the two compartments, then you get these just straight lines. Then there's a gap which corresponds to the menisci in these solution and solvent cells. They have to be dead matched. No point having a lot of solvent in and a bit of solution. They have to be matched exactly. So there's a little gap in the pattern corresponding to the menisci. And then what happens is that the fringes bend upwards depending on the concentration in the solution cell. Okay? So as the concentration builds up, the pattern will follow that concentration by bending upwards, just like with absorption optics. Oh, hang on. Where the concentration builds up. Right, where are we? Where are we? Here. Okay, so let's just so low concentration building up to high concentration. Each fringe profile reproduces a plot of concentration versus distance, and that's the meniscus, and that's the base of the cell. So the displacement of the fringes in the vertical direction is a direct measure of concentration. So we call the fringe displacement capital J. It's a bit like the absorption capital A For absorption optics, we've got the fringe displacement, capital J. For interference optics. And the same equations apply. Molecular weight is the rate of change of the log, natural log of the concentration with respect to the square of the distance from the center of rotation times a constant. So d log c dr squared, the slope of that times a constant gives the molecular weight. And once again, because it doesn't matter what the units of concentration are, because d log c dr squared is the same as 1 over c dc dr squared, so the units of concentration cancel. We don't have to convert our fringe displacement units, J, to weight concentration, C. There's no need to do it, okay? We don't need to know what the refractive increments and all these other parameters are, which we need to convert to weight concentrations. Not necessary. We can just work in fringe concentrations. So that's easy, and of course, if it's a polydispersed system, then we'll get a curve. We get an average slope, which gives you the weight average molecular weight. Yes, that's good. There's only one thing to be wary of, and that is our old friend non-ideality again. Okay, that's why we have to do non-ideality. You think, what's she doing that for? So we do non-ideality because it comes in all these types of measurements. So now we're trained, we can handle that. We know, yeah, we do that. We just extrapolate to zero concentration, or we just work at low concentration where these effects are negligible. So it happens time and time again with different techniques. So thermodynamic non-ideality, there's molecules getting in the way of each other or repelling each other. Values for the molecular weight so obtained at a finite concentration C are only apparent values because of non-ideality. So they're not the right answers, they're affected by non-ideality. But as they get closer and closer to the right answer, as we get more and more dilute. And in practice, for proteins, the apparent molecular weight is approximately the true molecular weight when you go to concentrations less than 1 milligram per mil. But for glycoconjugates and polysaccharides, even below 1 mg per mil, an extrapolation may be necessary. And what we do is we don't extrapolate the molecular weight directly, we extrapolate the reciprocal of the molecular weight against concentration, and we use this equation here. So one over m apparent equals 1 over m, the true molecular weight, is 1 plus 2b mc. So 2b or not 2b? That is the question. 2b or not to be in sedimentation equilibrium? Yes. The answer is yes. In osmotic pressure, 2b or not 2b? The answer is no. It's just b. Right? So the equation is very like the one we have for osmotic pressure, except that you've got a 2b here and not just a single b. This b is the second virial coefficient again, and that's the concentration. Note that we don't always use, I said before, and be careful about this, that Usually big C is the weight concentration and little c is the molar concentration, but not always. All right. Sometimes we use little c for weight concentration as well. So beware of that. Okay. And here I've used little c, but it's the weight concentration, right? And the other difference is that the molecular weight, instead of being a number average, which is what we get in osmotic pressure, it's the weight average. So it's the weight average molecular weight. Yep, equilibrium. I think that covers everything. Oh, apart from this. Yeah. So this is really useful. This helps you to understand what we've been talking about. So I'm sure you're very delighted the fact we've included this for you. Yes? Right, so this is the final question. This adds to the assess questions which you've got already. This is the sixth question, if you like. You've had the 5 questions on the sheets. This is the final question. So what you've got to do is the egg protein of albumin, that's a sensible choice, was examined by a sedimentation equilibrium experiment in the ultracentrifuge. The experiment at 25 degrees centigrade was observed using the interference optical system. So that's what we've just been talking about. And when the patterns measured, the following results were recorded for the fringe concentration C as a function of distance from the center of the rotor. So this is the distance from the center of the rotor, 6.87, 6.93. These are the concentrations in fringe units. That, by the way, is a 2, not a 1. Okay, I've probably badly written it there. That's a 2, so it's 0.24. So make sure you read it as a 2 when you do the question. Yes, 0.2, it looks like 2 to me, doesn't it? Yeah. Some people read it as a 1. So complete the table. That means using your calculator if you've got one, or maybe mobile phones use do logs. I don't know now, but or use it or do Excel if you have to. And plot R squared abscissa versus log EC. What's abscissa? That's right, the x-axis versus log C, which is the ordinate. Ordinate is the y-axis. Yeah, make sure you plot it correctly because you've got on the notes. It's clear. It's log C against R squared. Yeah. Evaluate the slope. What are the units? Bearing in mind what we've been talking about there. The buffer had a density of 1.0021 gram per mil and the specific volume is 0.746. Rotor speed was that. Look at that, I've even worked that out for you. You don't have to convert using the 2 pi over 60 rule. What do you estimate for the molecular weight of albumin? And we give you the R in CGS units, so don't use the SI units for R, use that value there. And don't forget T is the absolute temperature. So all you've got to do is accurately plot a graph and see how you get. And when we mark it, we'll be taking particular note of significant figures. Bearing in mind you only have 4 data points here, which can be quite noisy. So we'll be looking at the significant figures, which you will be presenting. Yeah, okay, it should be quite simple. You can do it on Excel or Origin or whatever. Beware of Excel, by the way. When you plot Excel, sometimes it truncates when it gives you the slope. It only gives you one significant figure. So make sure that your settings are correct if you're using Excel, or you can just plot it manually if you like. Then you've got to do logs on the calculator. And that's to be submitted at the same time, I think, as the other 5 questions.
Should we submit this with the other 5 questions?
I'll need to check what I did in previous years. I think they were all submitted together, but I'll confirm that for you. This is effectively question 6. Any questions on that? So if I showed you that at the start of the lecture, you'd think, oh gosh, you can't do that. That looks awful. But now we've gone through it in a careful sort of way, hopefully you should be able to do that. Remember, it's logs to base E, not logs to base 10. Otherwise, you get a molecular weight which is 2.7 times 2 big. Yeah, all right. If you use logs to base 10 without the correction factor. Okay, right. So what we do now is we'll stop the record. That was a good time. 3 minutes remaining. That was great timing. And we will